Hey guys, some of you might have seen those beautiful abstract pictures of those kind of stringy constructions. And what they are is they are strange attractors. And strange attractors are a set of formulas that always yield a similar kind of image, no matter what kind of starting values you input into that formula. It may sound complicated at first, but it's not as difficult as it may seem. In order to implement a strange attractor, we need two things. We need a set of formulas that forms the attractor, and we need an algorithm, kind of a method, to calculate value after value after value of these equations, and at the results of these equations, create certain points. So let's look at the algorithm first that we're going to use. And this is really a straightforward, a rather simple algorithm. It basically has only 3 steps. And the algorithm works like this. We start off with an active point. It's active, so I've drawn it in orange here. And through a given set of formulas, we calculate a new position of this point and create a new point at this position. So we have 2 points now. And the last step in our algorithm is we set the old point to non-active. So that as soon as we, with these 2 points, start the algorithm again from here, only from this active point, a new calculation gets done, a new point gets created, and this point gets set to non-active. So it's basically only these 3 steps. Take an active point, calculate its new position, create a new point at the new position, and set the old point to non-active. As for the formulas which will determine the new position of each point, there is quite a funny homepage called 3dmeyer.de. It's a German homepage, and it features a huge collection of formulas for attractors, and they are hidden under tutorials. And you have got this Attractors 1, Attractors 2, and Attractors 3. And what I found nice was to implement the so-called Diquan-Lee attractor, which we can see here, and it's gonna give this really nice threefold, fractalish, kind of symmetric appearance. First thing I'm gonna drop down is a geo node, dive in there, delete the standard geo, and with the help of the add sub, I'm gonna add a point. Just by checking this box, I'm gonna hide the grid and activate the point visualization. So I see here a point, and by hitting D over the viewport, I am gonna go into geometry and increase the point size so that we see the point we're operating on. And the first thing I'm going to create is a group. I'm going to do that with the group sub, drop that down here, wide up, activate it, and give the group a name of active. So this stores if a current point is active or not. And with the pattern, I'm just going to input the star, so everything that comes in here is already in the group active. Let's just look up in the geometry spreadsheet under points, and I haven't set it up correctly. I want it to be a point group, so let's choose points here. And now I see my point is 1 in the group active, so that means it's a member of the active group. Perfect. Now the next thing I want to do is calculate this point's new position based on given formulas. And I'm going to do that with a point wrangle node and with a bit of VEX code. So I'm going to drop down a point wrangle here, wired up, and I'm going to create some variables first. So variables are just constructs that can store a given value. And what I'd like to have are some float variables. Let's call them x, y, and z. Also, I'd like to have a vector called pos. And let's set this vector to 0, 0, 0. Exactly like that. So the vector is now 0, 0, 0. And also, now I gotta look that up at the Attractors homepage. I want these constants here, so I'm just gonna mark them here. Hit Command C. Gonna go back into Houdini. Just paste those here. And let's get this right. So each line needs to end with a semicolon. Just gonna take out the line breaks. This should be a point, not a comma. Oops, same goes for that, Semicolon at the end always. And of course I need to declare those variables first, so I need to tell VEX which type they should be. So either I can write float in front of each of them, but just gonna do it this way. Just add them here, A, B, C, D, E, K, and F. Like that. A, B, C, D, E, K, and F. Exactly. Okay, so I just initialized my variables. Let's check. Okay, no error messages this far, even when I highlighted. Perfect. Let's go back to that 3D homepage. And now what I need to input are those formulas. And we're just gonna start with the right part of the formula. And let me explain what that means. Do it like that. And I'm gonna type in here A times brackets y minus x plus d times x times z. And the next line should be this one here. So it is k times x plus f times y minus x times z, semicolon. And the last row is c times z plus x times y minus e times x squared, so I can write that as x times x. And what this expression on the left side of the formula means, that the position for the next step, so this is just the next time step, if you will. So the position x for the next time step equals this formula. So what we are going to do first is we're going to extract the points position x, y, and z from the pos vector. And what I'm going to do is write down first pos equals at p. So pos stores now the current point position. At p is an intrinsic variable that always stores the current point's position. And the next thing I'm going to do is write down x equals pos. And there are several ways how I can extract the x value. I can either write pos.x, or it's kind of old school, but that's how I like to do it. Square brackets and just a 0. The 0 is the first index of this vector. So 0, 1, and 2 are the indices of the vector. So this extracts the x position. Similar for the y position, only this time I do not want the 0 position of my vector, but I want the 1 position, which is the second. And I'm going to do that for z as well. Like that. So now I should have got my x, y, and z values in separate variables. So now what I can do is say x equals x plus, and let's put this in brackets. So I'm just gonna, for each time step, I will increase x by the value of this formula. Same for the y equals y plus brackets, and as well for z. Okay, the last thing I need to take care of is the time step, the dt, because at this moment I'm just stepping ahead one discrete time step, which might be really big for certain calculations. So I want to decrease the time step and make the steps smaller so that the resulting image has a denser point cloud, the denser point count. And I'm going to do that by, to this part of the formula, which is basically just this, or this part of the formula is just this. And I'm going to multiply this part by the time step called, let's call it dt. And in order to multiply it, I need to create dt, so I'm going to say create a float called dt as well, and set it up here. And say in our case, I can read that out of that homepage here. No, I can't even read it out of that homepage here. Sorry, my mistake. So I'm just going to guess a number first and then slowly iterate to something that makes sense, say 0.01, something like that. So let's see if I made any mistakes. No, that seems to work. Okay, now I did all the calculations, calculated the new position of that new point, so now I need to add a new point. And the way that is done in VEX is with the command addPoint, like that. And as function arguments, I give it the geometry ID, and in our point, this is the first input slot, which has the ID of 0. And then I'm going to give it its new point position, which I do not have at the moment, which I should create, and I'm going to use pause to store it. So I'm just going to say pause equals set, and then x, y, z. So I'm just going to pipe these newly created values for x, y, and z back into the position vector with this command. And I'm just going to add it here. That should be it. Okay, now I added the new point. Let's just check. Oh, this is kind of small. Let's see the IDs. So this is created at the same point the current point is. Let's check in the geometry here. Okay, and that is because we're starting on the 0 positions. So all of these formulas, they just add up to 0. So in order to get some more meaningful results, we can have a look at this part of this homepage where the author suggests certain input x, y, and z values. So we're just going to set them up by going into the add node and setting the point position accordingly. So 0.349, that is a 0, and this is minus 0.16, like that. And now I can see this is my first point, this is my second point. That seems to work. Okay, now before I go into detail about how to repeat that calculation over and over again, let's just take care of grouping those points accordingly. Because if you remember my drawing, I need to set the old point to not active so that only the newly created point is active and the old point is not active anymore. So let's do that by going into the VEX node, to the point wrangle. And for the newly created point, we need to add this to a group. And the problem with creating a point in VEX and then wanting to add this point to a given group is that I have no point ID at this moment. So I need to know which point ID is the ID of the newly created point. And I can do that by saying I want an integer. Let's call it new pt for new point, and it equals this value. Because the addPoint function does not only add a point, but it also returns an integer value containing the newly created point's point number. And we're going to use this within the next function, and this is called set point group, and we're going to use that to set this points group to active. So again, I need to tell it which geometry it belongs to, and that's the first input slot, so it's 0. Then I need to tell it which group it should belong to, and this is the active group. And then I have to look that up in the documentary. So that happens a lot when you're writing VEX. Basically, you're all looking up functions all the time. So you do that by clicking on the help button. So the help menu opens. And then what I'd like to do up here in the search bar, just search for VEX functions and click on that page. And now I have a huge list of all the functions that VEX has got for me. And the function I'm using at the moment is the setPointGroup function, so I'm just going to filter it. And I have it here, so click on it. And this is the documentation for that function. And it tells me which arguments the function needs. And the arguments are just those variables that the function needs to work properly. So in our case, the geohandle, which is a 0 input here, the string name of the group, which I have, the active, then the point number, so I'm going to put new pt here, then an integer value, so either 1 or 0, if it's in the group or if it's not in the group, so 1 in our case, and this is optional, the mode, if I want to set it or if I want to add it or whatever, and I can just omit that and it's just going to set that value. Final thing I need to do is tell the node that the old point where I'm coming from is not active anymore. So I'm going to do that again with a set point group function call. got like that. And again, 0 input, group name is active. This time we're taking care about the old point. In our case, this has the PT num, so remember this is the point we added, and this got the point number new PT. So my old point still has the current point number, which is accessed by add PT num. And we want this point not to belong to the group anymore, so let's set its group membership to 0. That should be it. Let's check. Okay, this executes. Let's have a look at the geometry spreadsheet, and we see the first point, the point with the point number 0, does not belong to the active group anymore, and the newly created point belongs to it. Perfect. So this is the fundamental algorithm for creating attractors. Let's just save that. And now let's take care of repeating this algorithm over and over again. And what I'm going to use for that is a solver node, which will exactly do that, execute a given set of nodes over and over again on the point data or on the data of the last solver step. So when I hit play now and just highlight this point triangle out of nowhere, it's not going to do much, because it's always repeating that same calculation on the same input point. But what I'd like to do is now feed back the output of this calculation into its input, and the solver node will exactly allow me to do that. So I'm going to wire the input up here, gonna shake off that point triangle there, just hit Control X, dive into the solver, Control V and paste it, wire it up, and that is it. So now, as soon as I'm going to dive up and hit play, just zoom out a bit, I am creating these, point. So zoom out a bit here, yeah, something like that. Just disable those and press D and scale the point size a bit smaller. So I see now we're creating points. Let that run a bit, stop. Let's have a look at what's happening here. So when I go into the geometry spreadsheet, I see for each step, for the first step, this is working correctly. I'm just going to create one new point. For the second step, I'm doubling that amount of points. For the third step, again, I'm doubling it. So this is running exponentially. So there's something wrong here. Let's dive into the solver and see what's happening here. Inside the point triangle, the thing that I was missing, that I did not do, is I didn't check which point is the active point. And I'm now running this piece of code on every point there is. So it gets slow, extremely fast, and it's creating a whole lot of points that I don't really need, because it's creating duplicates of points that I already calculated, and it's just messing up the whole setup. So what I need to do is check if the current point that we're working on is within the group active or not, and only execute all this code if the current point is in the group active. And I'm going to do that within VEX by just on the very top dropping down an if statement. So I say if brackets in point group, again that's a function, and just let me look up the function arguments again by typing VEX functions in here, going to it, and filtering for in point group. And again, the arguments it needs is 0 for the input, then the group name, active, and the point number we're looking for, in our case, PT num. If that is true, then curly bracket execute all the code, and we need to close it again, and just for the sake of readability, which is good practice, mark all that code which is in between those if brackets and just indent it one step. So now this piece of code, all the code, only gets executed if this function in point group returns a 1. And it will only do so if the current point, PT num, is within the group active. Okay, let's check again. And you see this runs a lot faster and generates many points. However, not enough points to give that image we're looking for at the end of a 240 simulation steps. And I mean, I could crank up the frames, but I'm just going to take care of that by highlighting the solver and giving it more substeps. So let's say, for example, 64 substeps. So for each frame, the solver will run 64 times. Like that. And at a certain point, it's creating this kind of erratic points here. So let's dive in again and check our code. And I suspect that my time step is still a bit too big, so let's decrease dt by the factor of 10 by just adding another 0 in front of the 1, going up 1 level, and run the simulation again. Perfect. And now it is yielding exactly that image that we've seen on 3D Maya's homepage. So it's this kind of symmetric shape. And what I'd like to do now is add line segments in between those individual points, so connect them to a spline. And we're going to do that by first creating a primitive, a polyline primitive. So after we group the node, let's add another point wrangle. And within those point wrangle, add a primitive with the add prim command. And again, I'm really bad at remembering function arguments, so help for me again. VEX functions, going to there, Googling for add prim, and it needs the geohandle and the type. So the geohandle is the 0 again, 0 input, and the type is a polyline, like that. And let's read out its internal ID by letting it output new prim. So it automatically will return the ID to the new prim variable. What I'm going to do next is add to it a vertex, so the first vertex in that polygon line. And I'm going to do that by the add vertex function, and the geohandle is 0 again. The primitive number is new prim, and the point number I'd like to add is current point pnum. So what I've done now is, when we go to the geometry spreadsheet, I've created a new primitive here, primitive number 0, which was not there before, and I already added the first point to it. Okay, now I need to fill it with all those other point positions that I'm going to calculate here in the solver. And I'm going to do that by going in here after I created the new point and set the groups correctly. I'm going to call the add vertex, and again it's the input slot 0. Also, I haven't created a new primitive, so it's still the 0 primitive, and I'm going to add to it the new point with new PT. So that should be it. Let's see. And as you can see here now, it's drawing this polylines between all those points. So I can turn off the highlighting and watch the algorithm draw out this beautiful shape. Yes, I'll maybe give it a bit more substeps so it might finish this part of the shape as well. So let's say increase it to 128 substeps, rerun the simulation. Something like that. Yeah, very nice. And there are several options on how I could render that. And I really like to use volumes to give this kind of a molten appearance. So what I'm going to do is first use the wireframe SOP to build a geometry out of these splines, and maybe increase the wire radius to something like that. So I now have this geometry. I'm gonna convert that into a VDB with the VDB from polygons node, and maybe set this to half of the size of the wire diameter and wire it up here, highlight that, and it takes some time to build that volume from all those splines. Something like that. And let's smooth this out a bit so it looks a bit molten together with a VDB smooth STF node. Wire it up here, highlight it, let it cook a bit. Maybe the iterations were a bit too much. Only 2 iterations. Yeah, and you see it melts those lines which are close together. Really nice. And let's convert that back to a polygon. And this is the polygonal mesh that we can now export and use to render it. Or we could render it here in Houdini in Mantra. Let's recap the algorithm. Let's recap what we did. First, we created a point, just a singular starting point. Then we set a point group. We set up a point group called active and added this first point to it. Then in this point wrangle, we created a new primitive, a polyline, and added the first point to it. And this is what we feed into the solver, which will repeat a given algorithm over and over again. And within that solver, I drop down this VEX code. And what it does is, first, it checks if the current point we're working on is active. And if that's the case, we're going through all of this code. So what we're going to do is we set up variables. We're setting up a variable for X, Y, and Z, which we're going to use for position calculations, and all those variables important for the formulas of the strange attractor, as well as a parameter called dt for the time step. Next is we're creating a vector, which we're going to set to 0, 0, 0. We set up our time step to this value. All of the necessary variables for the strange attractor formulas are set up here. And what we're doing then is we load the current point position into the variable called pos, and from it we extract its x, y, and z position. Based on the x, y, and z position, we calculate the next point's position by this strange attractor formula and scale it with the time scale factor dt and add it to the current point position. We are converting those 3 floats back into one vector called pos and create a new point at this position called pos. Then we set the point group of that newly created point to active and set that point group of the old point to inactive. And also we're adding this newly created point to the primitive that we created outside of the SOP, to the polyline. And within the solver, all of that code gets repeated and executed on the data it generates. So this is always run on the previous frame's data. So it keeps adding new points. So now that we have this general setup, what we can do is go to the 3D Maya homepage and have a look at other attractors that are there. And as you can see, all of those are pretty similar. For example, this one yields a totally different form, but has very similar formulas for doing so. So what we can do is go into Houdini and within the solver, exchange those formulas that we have. So let's just maybe make a copy out of that point wrangle here. Call this one Dikwon Lee. Whoops. And this one is gonna be Genesio TC. And in here in this point wrangle, we will set up those variables A, B, and C. Don't need those other variables here. And we're going to set up the formulas as well. So this should just be Y. This should just be Z. And this one here is minus C. times x minus b times y minus 8 times z plus x times x. Okay, let's check what shapes this is going to yield, and again I'll just set up a starting position of this formula, and I'm just going to use those values here, so it's going to be 0.1, 0.1, 0.1. Okay, let's check what this is yielding. Okay, this one is very small. So that's the thing with the strange attractors, they don't always have the same scale. So yeah, but this is slowly building this shape. What you can do now is just look out for any of those strange attractor formulas and just basically copy paste them into this construct that we built here. So you can try out many different attractors and different shapes that they're yielding, and there are many more. I think this homepage has a pretty good collection. I guess there are over 50 on there. So if you're intrigued by those 2 attractors that we quickly implemented here, just go to the 3D Meyer homepage, have a look at all the beautiful attractors that he collected, and modify the code that we've written here in order to get this beautiful collection of different shapes and different abstract shapes that these formulas can create. Again, I'm very excited to see what you guys come up with in your artwork. I hope you had fun with this, and cheers and goodbye.